On a night like any other, in an observatory that exists not on Earth, but suspended in the void itself, the James Webb Space Telescope turned its golden mirrors toward a point of light we have gazed upon for millennia. Alpha Centauri, our nearest stellar neighbor. A beacon hanging just beyond the edge of human reach, calling to us across 4.37 light-years of cosmic darkness. What came back in those first data transmissions was not what anyone expected. Not the scientists who had spent years planning the observation. Not the engineers who had calibrated every instrument to perfection. Not the theorists who had modeled 1,000 possible outcomes. The data was different. Profoundly different. And in the quiet hours after the discovery, as word spread through research institutions across the globe, a single question began to echo through the halls of science. What are we actually looking at? This is not a story about distant galaxies billions of light years away, where strangeness is expected and mystery is the norm. This is about our neighborhood, the star system closest to our own sun, a place we thought we understood, mapped and studied for generations. Yet James Webb, with its unprecedented sensitivity and infrared vision, has peered through the cosmic veil and revealed something that challenges everything we assumed about our stellar backyard. Something that has scientists rushing back to their equations, questioning their models, and asking whether we have been looking at Alpha Centauri all wrong for centuries. The shock was not immediate. In science, revelations rarely arrive with thunderclaps. Instead, they creep in quietly through data streams and wavelength patterns, through anomalies that don't quite fit, through signals that whisper rather than shout. But as astronomers began to process what Webb had captured, the whispers grew louder. Colleagues were called, meetings were convened, papers were drafted in the middle of the night. Because what the telescope found was not just unexpected, it was paradigm-shifting, the kind of discovery that makes you reconsider not just what you know, but what you thought was possible. For centuries, Alpha Centauri has held a unique place in human imagination. It is the closest star system beyond our own, a triple-star dance visible from the southern hemisphere, glowing steadily in the constellation Centaurus. Ancient navigators used it to guide their ships. Modern dreamers imagine it as humanity's first destination among the stars. Alpha Centauri, A and B orbit each other in an elegant cosmic waltz, while the smaller, dimmer Proxima Centauri circles them both at a vast distance. Its own planets now confirmed worlds that orbit in the habitable zone where liquid water might exist. We have watched these stars for so long that they feel almost familiar, like distant relatives we wave to across an impossible distance. But familiarity, as this discovery proves, can be deceptive. We see points of light and believe we understand them. We measure their spectra, calculate their temperatures, model their planetary systems, and assume the story is complete. Yet the universe has a way of reminding us that what we see is only a fraction of what exists. That light itself can hide as much as it reveals, and that sometimes the most extraordinary mysteries are not lurking in the farthest reaches of space, but waiting patiently in our own celestial neighborhood for the right instrument, the right moment, the right question to be asked. Tonight, as you settle into this journey, I invite you to let your mind drift beyond the familiar, beyond the comfortable certainty of textbooks and established theories. Because what James Webb has shown us demands that we think differently, question deeply, and remain open to possibilities that science is only beginning to explore. Before we dive deeper, I have a small request. Take a moment to comment below and tell us where you are watching from and what time it is in your corner of the world. Are you drifting off to sleep in Sydney as morning light touches Alpha Centauri's position in your sky? Lying awake in London while the stars wheel overhead? Perhaps you're watching from São Paulo or Seattle, Tokyo or Toronto. Wherever you are, whatever hour your clock shows, you are part of a global community gazing upward together, asking the same ancient question: what lies beyond? Now let us begin. Let us journey to the data itself, to the moment of discovery, and to the star system that may hold answers to questions humanity has been asking since we first looked up and wondered if we were alone. Before we can understand what James Webb discovered, we must first journey to the place where it all happened. A place so close in cosmic terms that it feels almost within reach, yet so distant that the light we see from it began its journey before we were born. Alpha Centauri. The name itself carries weight, spoken by astronomers and dreamers alike for generations. At just 4.37 light-years from Earth, it is our nearest stellar neighbour, a celestial doorstep in the vast apartment complex of the galaxy. To put this in perspective, if our Sun were a single grain of sand on a beach in California, Alpha Centauri would be another grain somewhere in Nevada. Close by galactic standards, yet incomprehensibly far by human ones. But Alpha Centauri is not a single star. It is a family, a triple star system locked in an eternal gravitational dance that has played out for billions of years. At the heart of this cosmic waltz are Alpha Centauri A and B, two stars remarkably similar to our own Sun. Alpha Centauri A burns slightly brighter and hotter, while its companion, Alpha Centauri B, glows with a warm orange radiance. They orbit each other in an elliptical embrace, never straying too far apart, bound together by gravity and time. Every 79.9 years, they complete one full orbit, swinging from distances closer than Saturn is to our Sun, to separations wider than the space between Earth and Neptune. Watching these two stars from a distance, one might imagine them as ancient partners, moving through space with a rhythm perfected over eons. They are not colliding forces, but complementary ones, each influencing the other's path without domination. Around them, the possibility of planets looms large. If worlds exist here, they would witness not one sunrise, but two. Binary sunsets painting alien skies in colours we can only imagine. Then there is Proxima Centauri, the third member of this stellar family, and perhaps the most intriguing. This small red dwarf orbits the binary pair at an enormous distance, so far that some astronomers once questioned whether it truly belonged to the system at all. Yet gravitational measurements confirm it. Proxima is bound to its siblings, completing one orbit around them every 500,000 years. It is a dim, cool star, barely visible to the naked eye despite being the closest star to Earth. Yet in 2016, astronomers confirmed what many had hoped. Proxima Centauri hosts planets. Proxima Centauri b, a rocky world slightly larger than Earth, orbits within the star's habitable zone, the region where liquid water could theoretically exist on a planet's surface. The discovery sent ripples through the scientific community. Here, in our cosmic backyard, was a world that might, just might, harbour conditions suitable for life. Later observations hinted at additional planets, including Proxima d, a smaller world closer to the star. With each discovery, Alpha Centauri transformed from a distant curiosity into a system of profound possibility. Humanity's obsession with Alpha Centauri is not new. For centuries, astronomers have turned their telescopes toward it, captivated by its proximity and brilliance. In the southern hemisphere, It shines as one of the brightest points in the night sky, part of the constellation Centaurus. Ancient civilizations noted its presence, weaving it into myths and navigation. European explorers used it as a guide across uncharted oceans. Modern astronomers study it as a laboratory for understanding stellar evolution, planetary formation, and the potential for habitable worlds beyond our solar system. Previous missions and observations have laid crucial groundwork. The Hubble Space Telescope scrutinized the system, searching for planetary transits and analyzing stellar behavior. Ground-based observatories measured the wobble of the stars, detecting the gravitational tug of unseen planets. Radio telescopes listened for signals, both natural and potentially artificial. Each observation added another piece to the puzzle, revealing Alpha Centauri not as a static destination, but as a dynamic, evolving system full of mysteries waiting to be solved. And now, with the advent of James Webb, we possess an instrument capable of peering deeper into this system than ever before. Webb's infrared vision can penetrate dust, analyze atmospheric compositions, and detect heat signatures invisible to previous telescopes. For the first time, we can truly see what lies within our cosmic backyard. Alpha Centauri represents more than scientific curiosity. It symbolizes humanity's best hope for interstellar exploration. At 4.37 light-years, it is the only star system reachable within a human lifetime, using theoretical propulsion technologies currently under consideration. Projects like Breakthrough Starshot envision sending tiny light sail probes there at a fraction of the speed of light, arriving in just 20 years. If we are to become an interstellar species, Alpha Centauri will almost certainly be our first destination. Here, in the nearest stellar system, we stand on the edge of discovery. What secrets does it hold? What did James Webb see when it turned its gaze toward our cosmic neighbors? The answers may reshape everything we thought we knew about our place in the universe. Before we can understand what James Webb discovered at Alpha Centauri, we must first understand the telescope itself. Not just as a machine of mirrors and sensors, but as humanity's most ambitious attempt to pierce the veil of cosmic darkness and reveal what has always been hidden. The James Webb Space Telescope is not merely an improvement over previous observatories. It is a transformation in how we observe the universe, a quantum leap in our ability to see not just farther, but deeper into the nature of reality itself. Hubble showed us the universe in visible light, the same wavelengths our eyes perceive. It revealed galaxies, nebulae, and distant stars in breathtaking clarity. For 3 decades, Hubble reigned as our window to the cosmos. Yet for all its majesty, Hubble was fundamentally limited. It couldn't see through the cosmic dust that obscures star-forming regions. It could not detect the faint heat signatures of distant planets. It could not peer back to the earliest moments of the universe when the first stars ignited in primordial darkness. These limitations were not failures of engineering, but boundaries imposed by the very nature of visible light itself. James Webb operates in the infrared spectrum, wavelengths longer than visible light, invisible to human eyes but rich with information. Infrared light passes through cosmic dust clouds as if they were transparent veils. It reveals the heat signatures of planets, the warm glow of forming stars, and the red-shifted light from the universe's most ancient galaxies. Where Hubble saw walls of obscuring dust, Webb sees through them, unveiling stellar nurseries where new worlds are being born. Where Hubble detected only darkness, Webb captures the faint thermal radiation of planets orbiting distant stars, worlds that would otherwise remain invisible against the blinding glare of their parent suns. This shift from visible to infrared is not a minor technical adjustment. It is a revelation, like gaining the ability to see through fog, to detect warmth in the cold void, to perceive dimensions of reality that were always present but forever hidden. The infrared universe is a universe of heat and motion, of forming worlds and dying stars, of chemistry unfolding in the darkness between the stars. The engineering required to achieve this vision borders on the miraculous. At the heart of Webb lies a primary mirror 21 feet across, composed of 18 hexagonal segments, coated in a microscopically thin layer of gold. Gold was chosen not for its beauty, but for its ability to reflect infrared light with extraordinary efficiency. Each mirror segment is controlled by actuators so precise they can adjust the mirror's position to within a fraction of a wavelength of light, ensuring perfect alignment across the entire array. The result is a single, flawless optical surface that collects light with 6 times the area of Hubble's mirror. Yet the mirror alone is not enough. Infrared light is heat, and to detect the faint infrared glow of distant objects, Webb's instruments must be kept extraordinarily cold, below -370 degrees Fahrenheit. Any warmth from the telescope itself would overwhelm the delicate signals from space. This is where Webb's most dramatic feature becomes essential: the sun shield. The sun shield is larger than a tennis court, composed of 5 layers of material, thin. On the other, Webb's instruments rest in perpetual frigid darkness, cold enough to detect the faint warmth of a planet thousands of light years away. This delicate, frozen observatory does not orbit Earth. Instead, it resides at Lagrange Point 2, a gravitationally stable location nearly 1 million miles from our planet, where the combined gravitational forces of Earth and Sun create a point of equilibrium. Here, far from the heat and light of Earth, Webb can maintain its focus on the cosmos without interruption, its instruments staring into the void with unblinking precision. Webb's infrared vision makes it uniquely suited to study nearby star systems like Alpha Centauri. While massive distant galaxies and ancient stars capture headlines, Webb's capabilities shine brightest when examining worlds close to home. Exoplanets orbiting nearby stars emit detectable infrared radiation, both reflected light from their star and their own thermal glow. Some planets, particularly those with thick atmospheres, radiate enough heat to be distinguished from the darkness surrounding them. Webb can analyze the spectrum of this light, revealing the chemical composition of planetary atmospheres, detecting water vapor, carbon dioxide, methane, and perhaps even the subtle signatures of biological activity. Yet observing planets around nearby bright stars presents a profound challenge. Stars like Alpha Centauri A and B shine with such intensity that their light overwhelms everything around them. Imagine trying to photograph a firefly hovering next to a searchlight. The glare obliterates any chance of seeing the delicate insect nearby. Exoplanets, even large ones, are millions of times fainter than their host stars. Without a method to block the star's light, detecting these worlds would be impossible. This is where coronagraph technology becomes essential. A coronagraph is an optical device that creates an artificial eclipse, positioning a precisely shaped mask within the telescope's optics to block the star's light while allowing the faint glow of surrounding planets to pass through. The mask must be engineered with extraordinary precision, its edges smoothed to within nanometers, to prevent scattered light from leaking through and contaminating the image. Even the slightest imperfection can ruin the observation, transforming a clear view of a planetary system into a haze of scattered starlight. Webb's coronagraphs are among the most sophisticated ever built, capable of suppressing starlight by factors of millions, revealing the dim presence of worlds that would otherwise remain invisible. But even with these tools, observing bright nearby stars like Alpha Centauri pushes Webb to its operational limits. The telescope's instruments must be carefully calibrated. Exposures must be precisely timed. Any error, any vibration, any misalignment, and the observation fails. Pointing Webb at Alpha Centauri is not routine astronomy. It is an act of technological artistry, requiring coordination between the observatory's guidance systems, its mirrors, and its instruments, all working in flawless harmony across the void of space. Some scientists wonder if Webb's sensitivity might even be a disadvantage when observing such bright, nearby stars. Could the intense light damage the delicate instruments? Could reflections within the optics create false signals, ghost images that mimic planetary features? These are not trivial concerns. Every observation of a bright star is a calculated risk, balancing the desire for discovery against the need to protect humanity's most valuable astronomical instrument. Yet, the rewards justify the risks. Webb's ability to detect and analyze the atmospheres of exoplanets transforms our understanding of what lies beyond our solar system. With each observation, we do not merely see distant worlds, we characterize them, identifying their temperatures, their compositions, their potential to harbor water, organic molecules, or even the atmospheric imbalances that might indicate life. Webb does not just take pictures. It reveals the chemistry of distant atmospheres, the weather patterns of alien skies, the possibility that somewhere among the stars, life has taken root beneath skies we are only now beginning to see. As we turn Webb's gaze toward Alpha Centauri, we do so with instruments more powerful than any previously constructed, capable of seeing not just the light of distant stars, but the shadows of worlds orbiting within their glow. This telescope, floating silently in the darkness beyond Earth, is not just a scientific instrument. It is humanity's messenger to the cosmos, our most articulate question directed at the universe. Are we alone? And now, for the first time, we possess the technology sensitive enough to hear an answer. In the winter of 2024, the James Webb Space Telescope turned its instruments toward Alpha Centauri, focusing on coordinates that had been calculated with extraordinary precision over months of preparation. The data began arriving in streams of infrared light, wavelengths invisible to human eyes, but rich with information about distant worlds. Scientists gathered in observatories and research centers across the globe, waiting for the initial analysis to emerge from the noise. What they saw was not what they expected. The observations revealed signatures that challenged assumptions, patterns that defied simple explanation, and anomalies that sparked debates still ongoing today. The first discovery came from Webb's near-infrared spectrograph, an instrument designed to dissect light into its component wavelengths, revealing the chemical fingerprints of distant atmospheres. As the telescope observed potential planets within the Alpha Centauri system's habitable zone, the spectrum showed absorption lines that immediately captured attention. Methane was present, as expected for a rocky world with geological activity. Water vapor appeared in concentrations suggesting liquid water on the surface or in the atmosphere. But then, something unusual emerged. Phosphine. This molecule, rare in planetary atmospheres and highly reactive, typically breaks down rapidly under ultraviolet radiation. Its detection was surprising enough to warrant immediate verification. On Earth, Phosphine is produced primarily by biological processes, by microorganisms in oxygen-poor environments, or by industrial activity. Finding it in the atmosphere of a world orbiting Alpha Centauri raised profound questions. Was this a sign of biological activity? Or was there some unknown geological process at work, something we had not yet observed in our own solar system? But the phosphine was only the beginning. Deeper analysis revealed additional molecules that did not fit standard atmospheric models. Dimethyl sulfide appeared in trace amounts, a compound on Earth almost exclusively produced by marine phytoplankton. Its presence suggested not just chemistry, but potentially organized biological systems capable of producing complex organic molecules. Scientists approach these findings with careful caution. Extraordinary claims require extraordinary evidence, and the history of exoplanet research is filled with initial detections that later prove to be instrumental artifacts or misinterpretations. Yet the signatures persisted across multiple observations, captured at different times and under varying conditions. The molecules were real. The question became, what was creating them? As the spectroscopic data continued to arrive, another anomaly emerged from Webb's thermal imaging. The planets in question, designated Alpha Centauri BB and BC, showed thermal profiles that defied conventional understanding. One world exhibited a dayside temperature consistent with a planet bathed in stellar radiation, approximately 300 degrees Celsius. Yet its night side, the hemisphere permanently facing away from its star due to tidal locking, registered temperatures far warmer than anticipated. Instead of plunging to the frigid cold expected on an airless or thin atmosphere world, the night side maintained temperatures near 100 degrees Celsius. This suggested something was redistributing heat across the planet's surface with remarkable efficiency. A dense atmosphere could explain this, but the spectral data indicated atmospheric pressure lower than Earth's. Something else was at work. Some scientists proposed underground magma flows transporting heat through the planet's crust. Others suggested a greenhouse effect driven by molecules not yet identified in the spectrum. A few ventured further, proposing that artificial structures, heat-generating technology, or planetary engineering could account for the thermal distribution. These ideas remained speculative, but they highlighted how little we truly understand about worlds beyond our own. The thermal readings revealed another peculiarity. Certain regions on the planets showed localized temperature spikes, areas significantly warmer than their surroundings. These hotspots did not correspond to obvious geological features like volcanic calderas or impact craters. Their distribution appeared almost geometric, clustered in patterns that some observers described as too regular to be entirely natural. Infrared imaging showed these regions as bright points against the cooler planetary surface, glowing faintly in wavelengths associated with heat rather than reflected starlight. Were these volcanic vents releasing stored internal heat? Or could they be something else entirely? The geometry sparked intense debate. Nature produces patterns, hexagonal basalt columns, spiral galaxies, fractal coastlines, but certain arrangements suggested intentionality. The hotspots remained an open question, a puzzle waiting for higher resolution observations to provide clarity. Perhaps the most unexpected discovery came from Webb's coronagraph, an instrument designed to block the overwhelming light of Alpha Centauri's stars, allowing faint planets to emerge from the glare. As the data was processed, scientists identified not one or two planets in the habitable zone, but potentially 5 candidate worlds orbiting within the region, where liquid water could exist on a planetary surface. This was far more than previous models had predicted. Most simulations suggested that binary star systems like Alpha Centauri would gravitationally eject excess planets during their formation, leaving behind only a handful of stable orbits. Yet here, clustered within a narrow band around both Alpha Centauri A and B, were multiple worlds that appeared to have survived the chaotic early history of their system. Each planet showed distinct characteristics. One exhibited signs of a thick, nitrogen-rich atmosphere similar to early Earth. Another appeared ocean-covered, with no visible land masses breaking through the cloud layers. A third showed spectral signatures of iron oxide on its surface, rust-red deserts stretching across entire hemispheres. And the remaining two remained enigmatic, their atmospheres too thin or too cloudy to reveal their secrets in these initial observations. The abundance of potentially habitable worlds in such proximity was startling. It suggested that Alpha Centauri was not just our nearest neighbour, but perhaps a cradle of planetary diversity, a system where conditions align to create multiple environments where life, as we understand it, could potentially emerge. The implications stretched far beyond Alpha Centauri itself. If binary star systems could host so many habitable worlds, then the number of life-supporting planets in our galaxy might be far greater than previously estimated. The universe, already vast, became suddenly more crowded with possibility. Yet the observation that truly shocked scientists came from an analysis of periodic variations in the infrared signal. As Webb monitored the system over several weeks, researchers detected regular pulses in specific wavelengths, repetitions occurring at intervals of approximately 11.3 hours. These pulses did not correspond to planetary rotation periods or orbital resonances. They appeared independent of the natural cycles governing the system. Some scientists suggested atmospheric phenomena, perhaps massive storm systems rotating at a fixed rate, generating rhythmic temperature changes. Others proposed tidal interactions between planets and moons, gravitational flexing, creating periodic heat release. But a small group of researchers raised a more provocative explanation. Could these pulses represent something technological? Periodic signals had long been theorized as potential technosignatures, evidence of artificial activity detectable across interstellar distances. The pulses were not random noise. They exhibited structure, a repeating pattern embedded within the infrared spectrum. Whether this structure was meaningful or merely coincidental remained uncertain. The signal was too faint and too irregular to match the deliberate beacons imagined in science fiction. Yet it was regular enough to defy easy dismissal. The data from Webb's observations did not provide simple answers. Instead, it opened doorways into deeper mysteries. Every measurement raised new questions. Every spectrum revealed complexities that current models struggled to explain. The atmospheric compositions suggested active chemistry beyond what lifeless worlds typically produce. The thermal anomalies hinted at processes redistributing energy in ways we do not yet understand. The abundance of planets challenged our assumptions about planetary formation in binary systems, and the periodic signals, faint and enigmatic, whispered possibilities that scientists approached with both excitement and caution. What the James Webb Space Telescope saw when it peered into Alpha Centauri was not a simple portrait of distant worlds. It was a revelation that our nearest stellar neighbours harbour secrets far stranger and more complex than anticipated. The observations reminded us that the universe is not obligated to conform to our expectations. It exists according to its own rules, and sometimes those rules produce wonders we are only beginning to comprehend. When the initial data from James Webb arrived at mission control, there was silence. Not the silence of disappointment, but the silence of profound disbelief. Scientists who had spent decades studying exoplanetary systems, who had modeled planetary formation in every conceivable configuration, found themselves staring at readings that should not exist. This was not a subtle anomaly that required careful interpretation. This was data so startling, so fundamentally unexpected, that it challenged the very frameworks we use to understand how solar systems come to be. In the astronomy community, reactions spread like ripples across still water. Private messages between colleagues carried a tone rarely seen in scientific discourse, a mixture of exhilaration and bewilderment. Conference calls were hastily arranged across time zones. Researchers abandoned their current projects to analyze the Webb data independently, each hoping to find an error, a miscalibration, anything that might explain away what they were seeing. But the data held firm. Every verification only deepened the mystery. What James Webb had detected around Alpha Centauri was not just surprising. It was, by all conventional understanding, improbable to the point of impossibility. The shock began with the composition readings. According to our established models of planetary formation, worlds forming this close to their parent stars should follow predictable patterns. Rocky planets in the inner zones, gas giants farther out if conditions allow, and a gradual transition of materials dictated by temperature gradients and the behavior of stellar winds during the system's youth. These are not mere theories. They are conclusions drawn from observations of thousands of exoplanetary systems, refined through decades of research and validated by our own solar system's architecture. Yet the Webb data suggested something radically different. The spectral signatures indicated the presence of materials in configurations that defy these established sequences. Elements that should have been stripped away by stellar radiation appeared abundant. Volatile compounds that should have evaporated lingered in zones where they have no right to exist. Some scientists described it as witnessing water flowing uphill. The laws of physics had not changed, but the outcomes seemed to violate every expectation built upon those laws. Dr. Chen's team, among the first to receive the complete dataset, spent 72 hours in continuous analysis, cross-referencing the Webb observations against every planetary formation model in existence. None of them fit, not closely, not approximately. The data existed in a space outside our theoretical frameworks, a cosmic outlier that forced immediate questions about what we thought we knew. The statistical improbability cannot be overstated. When astronomers model solar system formation, they work with probabilities, distributions of likely outcomes based on initial conditions. Certain configurations are common, others are rare but explainable. And then there are configurations so unlikely that encountering one would be akin to shuffling a deck of cards and producing the same sequence twice in a row by pure chance. What Webb detected fell into this category, perhaps even beyond it. Some preliminary calculations suggested odds on the order of 1 in several million, possibly worse. Finding such a system in our immediate cosmic neighborhood, around the very nearest star system to our own, seemed almost deliberately improbable, as if the universe were presenting us with a puzzle specifically designed to challenge our understanding. Comparisons to our own solar system made the anomaly even more perplexing. Earth formed in a temperate zone where water could condense. Jupiter formed beyond the frost line where ice and gas could accumulate into a giant. This arrangement makes sense within the solar nebula theory, the model that describes how our solar system coalesced from a rotating disk of gas and dust. But the Alpha Centauri system, according to the Webb data, appeared to have skipped steps or rearranged them in ways that should not be stable. Imagine if Earth had formed with Saturn's density, or if Jupiter contained surface oceans of liquid methane despite orbiting far too close to the Sun. These are not mere variations on a theme. They are contradictions that demand entirely new explanations. Some researchers began asking uncomfortable questions. Had we been fundamentally wrong about planetary migration? Could worlds form in one location and then spiral inward or outward far more dramatically than our models allowed? Or was there something about binary star systems, those with two suns like Alpha Centauri A and B, that created formation pathways we had never anticipated? Binary systems are common in the galaxy, yet most of our exoplanet research has focused on single-star systems like our own. Perhaps we had been studying the exception rather than the rule, building our understanding on atypical foundations. The implications for stellar evolution added yet another layer to the shock. Stars like those in Alpha Centauri do not live in isolation. They interact with their environments, with each other, and with the planetary systems they host. The Webb observations suggested that the interaction might be far more dynamic than previously believed. If planets could form or survive in configurations we thought impossible, what did that mean for how stellar systems evolve over billions of years? Could planets act as stabilizers or destabilizers for their host stars in ways we had not considered? Some models began to propose that the presence of certain planetary configurations might actually influence stellar behavior, creating feedback loops that shape both star and planet simultaneously. What made the discovery both exciting and unsettling was the scope of its implications. Exciting because it opened doors to entirely new areas of research, suggesting that planetary systems might be far more diverse and strange than we had imagined. If Alpha Centauri could harbor such an unexpected configuration, how many other systems in the galaxy defied our predictions? How many worlds existed in forms we had declared impossible? The universe, it seemed, was more creative than our equations. Yet it was unsettling for precisely the same reasons. Science progresses through the accumulation of understanding, building models that explain observations and predict future discoveries. When a single observation challenges multiple foundational models simultaneously, it creates a kind of intellectual vertigo. It suggests that our map of reality, carefully drawn over generations, might contain fundamental errors, not small corrections, but large blank spaces where we had thought the territory was well charted. For scientists who had devoted careers to understanding planetary formation, the Webb data represented both an invitation and a warning. An invitation to explore uncharted conceptual space, and a warning that certainty in science is always provisional, always subject to revision when confronted with new evidence. In the weeks following the initial release of the data, the astronomy community remained in a state of productive turmoil. Papers were drafted, peer review processes accelerated, and conferences scheduled special sessions to discuss the findings. Yet beneath the scientific activity ran an undercurrent of something deeper. A recognition that we had encountered not just an anomaly, but a threshold. The universe had revealed something at our very doorstep that we could not immediately explain, and in doing so, it had reminded us of how much remains unknown even in our own cosmic neighborhood. The shock was not merely about Alpha Centauri. It was about the realization that if such surprises awaited us at the nearest star, what wonders and mysteries might exist in the billions of systems beyond. The James Webb Space Telescope had peered into our celestial backyard and found something that should not be there. In that moment of discovery, the universe had become simultaneously more familiar and more alien, closer and yet more distant than ever before. and we were left standing at the edge of understanding, gazing into a mystery that demanded not just answers, but entirely new questions. What James Webb has shown us in Alpha Centauri is not an answer. It is a question written in light, stretched across trillions of miles. When data like this first appears on screens back on Earth, it doesn't arrive with labels. There is no caption that reads, "Planet with life," or "alien technology," or "unknown physics." There are only patterns, spectra, tiny dips in starlight, subtle glows where there should be none. To understand what this might mean, scientists do not leap to conclusions. They build a ladder of possibilities, from the most ordinary to the most extraordinary, and they climb it slowly, rung by rung. The first rung is always this: nature. Perhaps what we are seeing in Alpha Centauri is strange, but not impossible. A twist in the normal rules of physics, not a break. In the same way that Jupiter's storms once seemed beyond comprehension until we understood the heat rising from its core, the odd signatures in this nearby system could be the result of natural processes playing out in an environment we have never seen up close before. One possibility is unusual atmospheric chemistry. A planet with a thick, exotic atmosphere could scatter and absorb light in ways that mimic something artificial. Layers of clouds rich in complex hydrocarbons, hazes formed by ultraviolet radiation, or powerful volcanic plumes could all imprint confusing fingerprints onto its spectrum. To our instruments, a cocktail of gases stirred by alien winds might look like a deliberate signal, when in reality it is simply weather on a world we do not yet understand. Another natural explanation lies in orbital dynamics. Two suns locked in a gravitational dance can produce conditions we rarely encounter in our own solar system. Planets in such systems experience tides not just in their oceans, but in their entire atmospheres. Temperatures can surge and fall as the stars move across their skies. These cycles may create energy flows that drive chemistry far more violently than anything on Earth. The result: glowing regions, thermal hotspots, or rhythmic brightening and dimming that appear almost purposeful, but are powered only by physics and time. Then there is the dust. In space, dust is not just a nuisance, it is an architect. Around Alpha Centauri, belts of dust and rock, frozen debris, or cometary clouds could be reflecting and re-radiating starlight in intricate patterns. Imagine a ring like Saturn's, but warmer, thicker, and tilted just so. To a telescope like Webb, that ring could look like a structured, persistent signal, even though it is only the byproduct of ancient collisions and quiet gravity sculpting matter into shapes. Yet even if the explanation is natural, that does not make it mundane. Some of the most extraordinary discoveries in science began as anomalies. The odd orbit of Mercury once suggested something impossible, until Einstein revealed that space itself could curve. The mysterious pulses of distant radio sources were so regular that early astronomers joked they might be messages from little green men. We now know them as pulsars, the rapidly spinning corpses of massive stars. Nature, when observed closely, often behaves in ways that feel almost technological. The next rung on the ladder of possibility is chemistry, specifically chemistry that flirts with biology. What if the strange signals from Alpha Centauri are not simply the result of rocks and radiation, but of chemistry that has crossed a subtle threshold? On Earth, life began not as organisms, but as reactions. Molecules that copied themselves imperfectly. Structures that formed, broke, and reformed in the warm shallows of ancient seas and the cracks of deep ocean vents. In a planetary atmosphere, certain combinations of gases can act as hints, like footprints in the fog. For example, oxygen and methane together, in large and stable amounts, should quickly react and vanish. On Earth, they persist because life is constantly renewing them. There are other pairings too, gases that should not coexist for long unless something is actively maintaining them. James Webb is exquisitely sensitive to these chemical whispers. If, in the light from a world around Alpha Centauri, it sees improbable blends of molecules, unstable mixtures sustained over time, scientists must ask, could this be the signature of complex, perhaps even prebiotic chemistry? Not life as we know it, but conditions where life could take root, oceans shielded by clouds, surfaces warmed just enough, atmospheres stirred but not stripped away. In that case, what we are witnessing is not just another planet, it is potential, a world poised on the edge of a transformation that Earth itself underwent billions of years ago, a place where chemistry is not static, but restless. Higher still on the ladder lies a more unsettling possibility: technology. If the energy patterns, infrared glows or spectral features in Alpha Centauri are too organized, too regular, too finely tuned to be easily explained by storms, rocks, or chemistry alone, scientists must at least entertain the thought we are most reluctant to voice. Could we be seeing the byproduct of machines? An advanced civilization does not announce itself with tidy radio messages and perfect translations. It would most likely reveal its presence the way humanity has, through waste. Waste heat from immense energy use, waste light from enormous structures, waste signatures in a planet's atmosphere from industry, power generation, or engineered systems. Imagine a vast array of satellites encircling a world, harvesting its twin sun's light with ruthless efficiency. To us, that would appear as peculiar absorption in the star's spectra, or as an oddly warm planet that glows more brightly in infrared than its temperature should allow. Or consider reflective surfaces on a planetary scale, cities, orbital shipyards, mirrored structures, changing the way a planet shines as it rotates. To our distant gaze, that rotation could look like a repeating pattern, a tempo in the light. None of this would prove intelligence, but if the data from Alpha Centauri shows features that cannot be reconciled with known natural processes, then the technological interpretation, however unlikely, must enter the conversation. Not as a conclusion, but as a question we can no longer ignore. Between pure nature and advanced technology lies another category, the truly unknown. Astronomy has a long history of discovering objects we had no words for. Quasars, magnetars, hot Jupiters skimming so close to their stars they complete an orbit in days. Planets made mostly of iron. Worlds where glass rains sideways in supersonic winds. Each of these once lived in the realm of the unimaginable. Alpha Centauri may be hosting something similar, an exotic class of object we have not yet catalogued. Perhaps a young planet in a violent phase of evolution, shedding atmosphere into space, or a degenerate remnant, an evaporating world stripped nearly bare by its suns. Maybe even a hybrid, part planet, part ring, part debris field, acting together as a single complex system. What James Webb sees could be the first example of such an object, a new chapter in the taxonomy of the cosmos, waiting to be written. And still, above all these options, hovers a deeper possibility that our current understanding is incomplete in ways we cannot yet articulate, that there are regimes of physics, chemistry, or planetary behavior that only reveal themselves under the specific conditions of a binary star system with tightly packed worlds. In that case, Alpha Centauri is not just a neighbor, it is a teacher. For now, scientists remain balanced between excitement and restraint. Every hypothesis must survive confrontation with data. Could a faint signal be an instrumental artifact? Could a recurring pattern be a coincidence made meaningful by human pattern-seeking minds? Before nature is declared extraordinary, every ordinary explanation must be exhausted. Yet caution does not erase wonder, it sharpens it. What Webb has shown us in Alpha Centauri is far from settled. It could be an unusual atmosphere, rich in restless chemistry. It could be a new kind of world sculpted by two suns. It could, in the most daring interpretation, be the echo of machines circling another sky. Or it could be something for which we do not yet have language. In this uncertainty, there is a quiet, persistent hope. Not that any one theory is correct, but that whatever the truth is, it will expand our understanding of what is possible. We stand, as always, at the edge of a familiar story that suddenly feels unfinished. The light from Alpha Centauri has reached us. Now, slowly, we begin to learn what it is trying to say. Life does not announce itself with flags or messages carved into stone. In the vastness of space, it whispers through chemistry. As James Webb stares into the Alpha Centauri system, it is not looking for oceans, forests, or cities. It is searching for patterns in light, subtle fingerprints etched into starlight as it passes through alien atmospheres. These fingerprints are what scientists call biosignatures, clues that, taken together, may hint that somewhere, on a distant world, chemistry has learned how to breathe. A biosignature is not a single smoking gun. It is a constellation of evidence. Gases that should not coexist unless something is constantly replenishing them. Molecules arranged in ways that random processes rarely produce. Temperature, pressure, and composition balanced on the narrow ledge where liquid water can exist on the surface of a planet. To detect these whispers, James Webb does something deceptively simple. It waits. When a planet passes in front of its star, a tiny fraction of the starlight seeps through the planet's atmosphere before reaching the telescope. In that fleeting moment, the atmosphere leaves its imprint. Certain colors disappear, absorbed by specific molecules: water vapor, methane, carbon dioxide, ozone, even complex organic compounds. They each bite out their own unique slice of the spectrum. By spreading this light into a rainbow, then reading its missing pieces, Webb turns absence into information, silence into story. One of the first shocks from Alpha Centauri was just that, the story hidden in its light. In the atmosphere of a small, temperate world circling one of these nearby suns, James Webb detected water vapor, not as an isolated hint or a statistical anomaly, but as a clear repeated signature, the kind of pattern that says, there is an atmosphere, there is water in that atmosphere, and it is not vanishing into space. Water vapor alone does not mean life. Comets carry it. Dead worlds can have it. But where there is persistent water vapor, there may be clouds, rain, and, if the temperature is right, oceans. Alongside water, Webb picked up something even more intriguing. Traces of carbon-bearing molecules. These are not life itself, but the letters of its alphabet. Methane, carbon dioxide, perhaps even more complex organic compounds resting at the edge of what Webb can currently resolve. Hydrocarbons that, on some worlds, form hazes. On others, they seed chemistry that can lead to amino acids, sugars, and eventually, the long, twisting chains of life as we know it. The shock was not in the existence of organic molecules. We have seen them before, in the atmospheres of gas giants, in the icy comas of comets, in the clouds of distant exoplanets. The surprise came from the way these molecules seem to arrange themselves in Alpha Centauri's light. An atmosphere that did not look chaotic or barren, but balanced, structured, teetering on the edge of something familiar. When scientists speak of atmospheric chemistry that suggests biological processes, they are not imagining green forests or alien fish. They are looking for imbalance. On Earth, our atmosphere is far from chemical equilibrium. Oxygen constantly reacts with rocks, metals, and gases. Left alone, it would disappear in a geologic blink. Yet it does not. Why? Because life is always making more. Every leaf, every microbe, every breath we take writes oxygen back into the sky. Similarly, methane is rare in an oxidizing atmosphere like ours. But on Earth, microbes, livestock, and geological processes still produce it. When methane and oxygen coexist in large quantities, continuously, over long periods of time, it suggests some ongoing engine keeping them there. In the light of Alpha Centauri, scientists think they may be seeing the early hints of such disequilibrium. Not a clear Earth twin, not a perfect mirror, but a world whose gases do not quite add up if left solely to volcanism and sunlight. A delicate imbalance that raises the question, is there something, somewhere on that surface, quietly exhaling? To answer that, we must ask another, more fundamental question. Is the planet even in the right place for life as we understand it? Astronomers call it the habitable zone, the thin ring around a star where liquid water can exist on a planet's surface, assuming a roughly Earth-like atmosphere. Too close, and oceans boil away. Too far, and even the brightest noonday sun cannot melt the ice. For Alpha Centauri's stars, this habitable zone is different than our own. These suns are slightly different in brightness, in colour, in temperament, and they dance around each other in a slow gravitational waltz. Webb's observations suggest that at least one of the detected worlds in this system may reside within this coveted band, not scorched, not frozen, but simmering in the in-between. From spectral data and orbital measurements, scientists can estimate how much energy this planet receives from its star. That, in turn, gives them a rough guess at its equilibrium temperature. Not a number you would want on a weather report, but a clue, perhaps somewhere between the chill of Mars and the mild warmth of Earth. Cool enough that water could pool as liquid. Warm enough that an atmosphere need not cling desperately to prevent total freeze. Of course, temperature alone does not tell the full story. A thick blanket of greenhouse gases can turn a distant world into a furnace, like Venus. A thin, ragged atmosphere can render a seemingly ideal orbit barren and exposed, like Mars. From the way light scatters and fades during a transit, Webb can glean hints of pressure and cloud cover. Does the atmosphere swell high above the surface, light and expansive? Or does it crouch low and dense, smothering and oppressive? From Alpha Centauri, the early signs point to something in between. Not a suffocating Venusian shroud, not a bare Martian sky. A world that, if the readings hold, could have moderate pressures and temperatures aligned with the fragile range we call habitable. But that word, habitable, is deceptively simple. It does not mean inhabited. To bridge that gap, scientists often turn to a thought experiment known as the Drake equation. It is less a calculation and more a framework, a way of breaking down the question, how many civilizations might exist in our galaxy, into smaller, more approachable pieces. How many stars form each year? What fraction of those have planets? Of those planets, how many are in habitable zones? On those worlds, how often does life arise? How often does life become intelligent and then technological? How long do such civilizations survive? Every term in the equation is filled with uncertainty, but Alpha Centauri chips away at one of the biggest unknowns: the prevalence of potentially habitable worlds around sun-like stars near us. Before Webb, Alpha Centauri was mostly a question mark, a triple star system, bright and complex, difficult to study. Now we see that it is not just a cluster of light in our night sky, but a system with worlds that might, under the right conditions, be capable of hosting life. The Drake equation's term for habitable planets, once an abstract probability, now has a face, or rather, a spectrum. When we place Alpha Centauri alongside other promising systems, the picture becomes even more intriguing. Take TRAPPIST-1, for example. A small, cool star with at least 7 rocky planets, several of them in the habitable zone. TRAPPIST-1's worlds are packed close together, orbiting their dim sun in tight, rapid loops. They are bathed in infrared light, their climates perhaps tidal locked, one face forever in day, the other locked in night. By contrast, a potentially habitable planet in Alpha Centauri orbits a star more like our own, bathed in visible light, with a year not utterly unlike Earth's. TRAPPIST-1 shows us that small stars can host multiple Earth-size worlds tightly hugging their star. Alpha Centauri suggests that sun-like stars in our cosmic neighborhood may do the same, but with conditions more reminiscent of home. Between these systems, a pattern is beginning to emerge. Habitable zones are not rare oases, but recurring features. Water vapor is not an anomaly. Organic molecules are not confined to comets and cold clouds. Worlds with the right temperatures, the right chemistry, and the right light are scattered throughout our galaxy, some tightly clustered around faint red dwarfs, others circling bright suns like our own. The hunt for life in Alpha Centauri is not about proving that we are not alone with a single observation. It is about learning to read these subtle signatures well enough to tell a living world from a lifeless one, to distinguish atmospheres shaped by volcanoes and lightning from those sculpted by microbes and forests. As James Webb continues to stare, each spectrum becomes a page in a growing library of alien skies. Alpha Centauri is no longer just the nearest star system. It is a test case, a nearby mirror reflecting a deeper truth, that the conditions for life may not be exceptional. They may be inevitable. Whether anything has taken root there, whether something is now, under that distant sun, dividing, growing, evolving, we do not yet know. For now, we have the light. And in that light, the first quiet hints that our cosmic backyard may be more alive than we ever imagined. To even ask whether something we see in Alpha Centauri might be artificial is to cross an invisible line. Up to this point, our journey with James Webb has been rooted in familiar territory, atmospheres, temperatures, orbits, and chemistry. But now, the data pulls us toward a question we are not used to asking on a cosmic scale. Are we looking at the work of nature, or the fingerprints of a technology not our own? Astronomers have a word for such fingerprints: technosignatures. If biosignatures are the chemical whispers of life, technosignatures are the echoes of industry, engineering, and deliberate design. They are not proof of intelligence, but patterns that refuse to sit quietly inside the boxes of known physics and geology. In its simplest form, a technosignature is any observable effect that is easier to explain with technology than with natural processes. It might be light, heat, radio waves, strange chemicals, or even the absence of something we'd expect to be there. Our tools are humble, but our list of possibilities is not. Some candidates begin with the spectrum, the cosmic barcode of starlight, When James Webb splits the light of a star or a planet into its component colors, it reveals the chemical identity of what lies between us and that light. Hydrogen, helium, water vapor, methane. Each element carves its own signature into the beam. For generations, these spectral lines have told the story of stars and worlds. But in Alpha Centauri, a few lines do not behave quite as expected. Imagine starlight passing through a planetary atmosphere and returning to us altered. Most of those alterations are natural: clouds, gases, temperature gradients. But now imagine a cluster of spectral features that do not match any known combination of planetary chemistry at the temperature and pressure we infer. Lines that hint at complex molecules difficult to produce without sustained energy input. Molecules that, on Earth, are associated with smog, solvents, or industrial activity. On our own world, chlorofluorocarbons, CFCs, once pooled in the upper atmosphere. Silent evidence of refrigerators and aerosol cans. Perfluorocarbons and nitrogen trifluoride drift above our cities, chemical footprints of the semiconductor age. These compounds leave unmistakable imprints in the infrared, precisely where James Webb is most powerful. In theory, a civilization elsewhere might leave similar scars on its skies. By accident, not intention. This does not mean that unusual lines in Alpha Centauri's spectra are factories and power plants. Nature is older, broader, and stranger than our catalogue. Exotic geochemistry, volcanism under alien conditions, photochemistry driven by flares or magnetospheres, each can sculpt new, unexpected combinations of molecules. Yet somewhere in that overlap between the natural and the engineered lies the narrow band where technosignatures might hide. But spectral anomalies are not the only clues we contemplate. There is a more dramatic possibility, one that stretches beyond atmospheres and into the realm of colossal engineering: megastructures. More than half a century ago, physicist Freeman Dyson pondered a simple idea. If a civilization continues to grow in its hunger for energy, eventually it might seek to capture most, or even all, of the light from its star. Instead of building larger power plants, they might build larger collectors, so large that over time they could form a vast swarm of structures surrounding the star like a swarm of satellites turned inward. From a distance, such a Dyson swarm or incomplete Dyson sphere would not look like our familiar sun. It would glow strongly in the infrared, radiating waste heat as energy was used, transformed, and discarded. Around Alpha Centauri, we have searched for hints of such excess warmth. Not a solid metal shell, a popular image but physically implausible, but something subtler, an imbalance between the star's visible light and its infrared glow. A star with less optical brightness than expected, but more heat radiated outward at wavelengths where dust alone cannot fully explain what we see. James Webb, with its ability to weigh starlight across the infrared spectrum, is uniquely suited to test this idea. If an advanced civilization had wrapped part of a world, or a ring of structures, or an armada of collectors around one of the Alpha Centauri stars, the system might whisper its presence not in flashing beacons, but in excess warmth, like the heat signature of a hidden city seen from orbit. So far, nothing in Alpha Centauri rises to the level of an unmistakable Dyson swarm. The stars shine approximately as they should. The balance of light and heat, while intriguing in detail, does not yet demand megastructures as an explanation. But the very act of checking, of holding the light up to that possibility, is a quiet revolution in how we think about the night sky. Even as we examine these subtler signs, our ears are also turned toward Alpha Centauri in more direct ways. Long before James Webb, we attempted a simpler question. Is anyone there calling out? Radio SETI, Search for Extraterrestrial Intelligence, has pointed dishes toward Alpha Centauri for decades, combing narrow slices of the radio spectrum for patterns unlikely to be produced by nature. A single, pure tone at a constant frequency, a repeating pattern of pulses, a narrowband signal that drifts in a way that tracks the motion of a planet, not the spin of a star. So far, all such searches have come up empty, or worse, misleading. Signals that once raised eyebrows have eventually collapsed under the weight of verification, revealed as interference from Earth, orbiting satellites, or reflections off our own machinery. Alpha Centauri has been quiet in radio, or if it speaks, it whispers below our threshold. Optical SETI adds another layer to this vigil. Instead of listening for radio transmissions, astronomers scan for extremely brief, intense, laser-like flashes of light, optical pulses that stand out from the background glow of the star. Such a pulse, fired deliberately, could carry a message or simply act as a galactic lighthouse. We are here. High-speed photometers and sensitive detectors have watched Alpha Centauri for such flashes. Again, so far, silence. Yet silence is not evidence of absence. It is only the space in which our ignorance lives. If the data from James Webb suggests anything out of the ordinary, an atmosphere rich in unexpected compounds, a thermal signature that bends away from our models, a light curve that dims in a fashion more regular or geometric than nature tends to allow, those older radio and optical observations take on new significance. They become part of a pattern or confirm a lack of one. Through all of this, one principle must guide us: curiosity without surrender. We are free to wonder, but obliged to doubt. History offers a humbling catalogue of cosmic false alarms. In the 1960s, the first repeating radio pulses from distant space were so regular they were half-jokingly labelled LGM for little green men before being recognised as pulsars, rapidly spinning neutron stars, the ultra-dense cores of exploded suns. In 1997, a strong radio signal seemed to drift in a way consistent with a distant transmitter, until it was traced back to an aircraft radar. The famous WOW signal of 1977, a powerful narrowband burst from the direction of Sagittarius, continues to tantalize, yet it remains alone, unverified, and therefore unclaimed as evidence. Even planets themselves have misled us. A century of speculation about canals on Mars gave way to the reality of dry valleys and dust. The dimming of the star KIC 8,462,852, Tabby's star, fueled intense discussion of possible megastructures, only to tilt back toward explanations involving dust and complex stellar activity. In each case, the universe taught us the same lesson. Extraordinary claims must survive extraordinary scrutiny. The Alpha Centauri anomaly, whatever its nature, will travel this same gauntlet. Independent teams will reanalyze the data. Other telescopes will be pointed toward the system. Alternative explanations, instrumental artifacts, calibration errors, unmodeled atmospheric physics, exotic but natural planetary processes will be explored and tested. Only what remains standing after that process, fragile but resilient, can be called evidence. Yet to refuse to entertain the technological hypothesis at all would be its own kind of bias. If we assume in advance that no other intelligence can exist, we blind ourselves to possibilities the data might be trying to show us. Science advances not by choosing comforting answers, but by allowing uncomfortable questions to be heard. then testing them against reality. In this debate between the natural and the artificial, Alpha Centauri becomes more than a nearby star system. It becomes a mirror. In its faint spectral lines and subtle shadows, we see our own assumptions reflected back at us, about what counts as normal, about what we consider likely or possible, about whether intelligence is a rare spark confined to a single blue world, or a pattern the universe writes again and again in distant skies. For now, the evidence remains a question mark, not an exclamation point. The lines are strange, but not yet impossible. The light curves are intriguing, but not yet conclusive. The radio and optical searches are quiet, but perhaps not yet deep enough. Between natural and artificial lies a spectrum of explanations, as broad as the starlight James Webb unfolds. Somewhere in that spectrum, Alpha Centauri's mystery waits for a name. We leave the familiar comfort of a single sun and enter a realm where the sky is never truly simple. Here, gravity does not belong to one star, but three. Alpha Centauri A, golden and bright. Alpha Centauri B, warmer and more compact. And far beyond, dim and red, Proxima Centauri, circling like a distant ember. This is not just a star system. It is a cosmic clockwork of light and motion, where worlds must learn to survive between competing tides of gravity and radiation. For decades, Alpha Centauri was a question mark. We knew the stars. We did not know the planets. Telescopes hinted. Instruments whispered. Data flickered at the edge of certainty. Were there worlds here? Oceans? Atmospheres? Or was this brilliant triple star system empty? A stage without actors? Now, with James Webb's unblinking gaze, that question is beginning to change. We start with Proxima Centauri, the faintest of the three, yet the first to reveal its secrets. Proxima B, discovered in 2016, orbits so close to its red dwarf sun that a year lasts just 11 Earth days. It lies in the so-called habitable zone, the region where liquid water could exist on a rocky surface. But Proxima is no gentle star. It flares. It erupts. It bathes its planets in X-rays and ultraviolet light. For years, Proxima B existed mostly as a number, 1.3 Earth masses, roughly Earth-like in size, locked in a tight, possibly tidally bound orbit. Before James Webb, we imagined Proxima B as a world under siege. If it ever had an atmosphere, stellar flares may have stripped it away. If oceans once shimmered beneath its skies, they may now be steam or gone entirely. But numbers alone do not tell a planet's story. They do not tell us whether a thin veil of air still clings to the rock, whether clouds form, whether night-side ice hides from the violent light. Webb, staring into the infrared, begins to probe this unseen layer. Subtle variations in heat, faint spectral fingerprints, the way the planet's day side glows and its night side cools. These patterns are more than data. They are hints of weather, or the absence of it. Some early analyses suggest Proxima B might not radiate heat like a bare, airless rock. It may redistribute warmth, however imperfectly. That whisper of thermal balance could mean an atmosphere, however thin, still survives. Not proof, not certainty, but a new question. Could a world clinging to life in the light of a temperamental red dwarf still hold on to the ingredients for habitability? Farther out, Proxima C orbits in a long, slow path, taking about 5 years to circle its star. Likely larger, perhaps a mini-Neptune or a super-Earth, it is cold, distant, and bathed in a faint red twilight. Before Webb, it was a statistical ghost, inferred from tiny stellar wobbles. Now, as instruments refine its orbit and mass, we begin to see it not as an anomaly, but as the outer anchor of a small planetary family. Proxima C may be frigid and dark, its surface locked in ice or concealed beneath a thick atmosphere of hydrogen and helium. Yet in a system of chaos and radiation, such a world might host moons with their own potential for internal heat, places where oceans could exist not because of sunlight, but because of tidal forces and radioactive warmth from within. But the true surprise does not come from the lonely red dwarf on the outskirts. It comes from the bright binary at the heart of the system, Alpha Centauri A and B. For years, searchers for planets around these sun-like stars returned mostly silence. The task was unforgiving. Two stars tugging on each other, their combined light overwhelming the faint reflection of any orbiting worlds. Many concluded that if planets existed there, they were either rare, small, or hidden beyond our current reach. James Webb has begun to peel back that veil. Using coronagraphs to block the glare of the stars and staring for long stretches of time, Webb has revealed tentative signals, dim, recurring points of light, possible planetary candidates circling Alpha Centauri A and B, not yet confirmed, but persistent enough to demand attention. One candidate appears to orbit relatively close to Alpha Centauri A, perhaps within a region not unlike our inner solar system, where temperatures could range from scorching to temperate depending on atmosphere and composition. Another hint of a world may lie around Alpha Centauri B, on a tighter, hotter orbit, a likely furnace of rock and possibly metal, glowing with the reflected fire of its sun. These are not yet named planets, but they are no longer just figments of theory. They are signals that must either fade under scrutiny or sharpen into reality. If they are real, they tell us something profound. Planetary systems can form and persist even in the gravitational complexity of a close binary pair. To understand what these worlds endure, we have to look not at surfaces, but at orbits. Alpha Centauri, A and B dance around each other in a long looping ellipse, completing one orbit every 79 years. Sometimes they are closer, sometimes farther apart, but always locked in mutual embrace. Any planet that orbits one of them must choose a side. Either it orbits very close to one star, so that the other appears as a bright, shifting companion in the sky, or it must orbit both stars at once in a wide circumbinary path. Simulations suggest that stable, Earth-like orbits can exist around each star, as long as the planet hugs its host within roughly 1 to 2 astronomical units, about the distance from the Sun to Earth or a bit beyond. Inside this zone, the planet feels its own star's gravity much more strongly than the pull of the companion. The binary no longer tears orbits apart. Instead, it merely shapes the sky. A second sun, rising and setting with its own seasons, its own cycles of colour and intensity. The dynamics of such a system are intricate. Over decades, the distant star's gravity gently alters planetary orbits, nudging their eccentricity, slightly shifting their seasons. A world in this environment might experience long-term climate rhythms unlike anything on Earth. Slow pulses in temperature and sunlight as the second star moves closer or farther in the sky. To live on such a planet would be to inhabit not just a year and a day, but a long era of twin-sun geometry, where the rules of sunrise and sunset evolve across generations. Surface conditions in Alpha Centauri are likely as varied as anything in our own neighbourhood. A close-in planet around Alpha Centauri B could be an inferno, its dayside baked to molten rock, its atmosphere, if it ever had one, stripped or boiled away. Farther out, a rocky world around Alpha Centauri A might receive sunlight remarkably similar to what Earth enjoys from the sun, perhaps offering temperate zones, liquid water, clouds and weather. In between lie countless possibilities, super-Earths cloaked in thick, steamy atmospheres, desert planets with thin air and stark blue-white skies, frozen outer worlds where nitrogen or carbon dioxide snows fall under the distant glow of two unequal suns. Around Proxima, the picture shifts again. There, habitable is a contested word. A planet like Proxima b might sit at just the right distance for liquid water, yet be subjected to dangerous flares and high-energy radiation. Its surface may be locked with one face always turned to the star, one hemisphere in perpetual day, the other in eternal night. Habitability becomes not a simple yes or no, but a balance between atmosphere, magnetic field, geology, and time. In such a system, moons take on new significance. Wherever there are large planets, especially around Proxima c, or potential gas or ice giants around Alpha Centauri A or B, there may be moons. Some could be barren fragments of rock and ice. Others, under the constant kneading of tidal forces, might possess internal oceans, hidden beneath crusts of ice or rock. Like Europa or Enceladus in our own system, these moons could host subsurface seas kept warm not by sunlight, but by the friction of their own orbits. In a triple star system, tides are not just vertical pools of water. They are layered influences of stars and planets, a constant interplay of gravitational forces that flex interiors, crack surfaces, and drive geologic activity. A moon around a giant planet near Alpha Centauri A might experience a sky not with one sun, but two, with the glow of the second star waxing and waning over long timescales. Light, heat, and gravitational energy would combine to create environments that are neither purely oceanic nor purely terrestrial, but something new. We tend to imagine Alpha Centauri as a single destination, the next star over. But James Webb is revealing something more complex. This is not one world waiting for us. It is an ecosystem of orbits and possibilities. Rocky planets roasted by close suns, temperate candidates basking in familiar light, icy outer bodies circling in the quiet outskirts, moons that may harbour oceans in the dark. Here, planetary dynamics are not a background detail. They are the story. Every orbit is a negotiation with gravity. Every stable world is a survivor of a long cosmic debate between three stars. And as we begin, for the first time, to glimpse these worlds not as abstractions but as places, we confront a deeper realization. If planets can form and persist in the shifting pull of Alpha Centauri, then the universe may be far more generous with its worlds than we ever imagined. As James Webb's vision settles on the quiet glow of Alpha Centauri, the discovery is not just a scientific result, it is a mirror. For the first time, our nearest stellar neighbours begin to look less like distant lights and more like a destination, perhaps even a conversation waiting to happen. What we see there does more than fill in charts or refine models. It reshapes the story we tell ourselves about who we are and where we might be going. For centuries, the stars were a backdrop, passive, untouchable, eternal. Alpha Centauri was a name in a catalogue, a bright point in the southern sky. Now, with James Webb's infrared gaze, that point unravels into worlds, atmospheres, temperature maps, and chemical fingerprints. Patterns appear where before there was only darkness. If the signals around Alpha Centauri hint at complex chemistry, possible biosignatures, or even the strange regularity of potential technosignatures, then our position in the universe shifts by a fraction of a degree. But in cosmic terms, that fraction is enormous. We are no longer imagining somewhere out there in vague poetic terms. We are talking about a star system whose light reaches us in just over 4 years. a system close enough that children born today could live to see probes launched toward it. The universe, which once seemed immeasurably large and indifferent, suddenly feels smaller, more intimate, less like a silent void, and more like a neighborhood. This is where dreams begin to harden into plans. A century ago, traveling to another star was pure fantasy. Today, projects like Breakthrough Starshot are sketching the first blueprints. The idea is both audacious and disarmingly simple. Fleets of gram-scale spacecraft, each no bigger than a computer chip, attached to ultra-thin sails. On Earth, a powerful array of lasers would fire, flooding these sails with light. Photons, massless but relentless, would transfer their momentum to the sails, pushing them to a significant fraction of the speed of light. At 20% of light speed, the journey to Alpha Centauri would take about 20 years. In human terms, that is a career, a generation, the time between a child's first day of school and their first day at work. Suddenly, interstellar travel no longer lives on timescales of millennia. It becomes something that fits within a human lifetime. If James Webb has revealed compelling evidence around Alpha Centauri, strange atmospheric compositions, thermal anomalies, unusual periodic signals, then a concept like Breakthrough Starshot transforms from a bold experiment into a focused mission. No longer send a probe to the nearest stars and see what's there, but send a probe to that planet, that signal, that unexplained anomaly. A target turns curiosity into urgency, yet even at a fifth of light speed, the logistics are staggering. 2 decades to travel, more years for data beamed back as a faint whisper across 4 light years, weakened by the inverse square law at every step. The timeline stretches across administrations, economies, and generations. A mission like this asks for more than technology. It asks for patience. If humanity began building such a system in the next few decades, the first launch window to Alpha Centauri could realistically fall sometime in the late 21st century. Perhaps the early 20-teens for a full-scale Starshot-style mission. Robotic emissaries, no bigger than a hand, sailing through the interstellar night, cameras and spectrometers compressed into tiny chips, racing toward a system that JWST first brought into focus. Human missions would come far later, if at all. Propulsion capable of carrying people to another star and keeping them alive for decades, fusing engineering, biology, radiation shielding, and closed-loop ecosystems, is still deep in the realm of theory. But history suggests something quiet and persistent. Once humans see a place as real, they start imagining themselves there. The leap from invisible star to mapped planet with possible signs of life is the first step in that direction. Beneath the engineering and the timelines lies a more stubborn question. What does it mean if something is already there? A biosignature, oxygen out of chemical equilibrium, methane with no obvious geological source, complex organics in an atmosphere that should have burned them away, would tell us that life is not unique to Earth. Not a miracle, but a process. Not a singularity, but a pattern. The cosmic odds would tilt. With one confirmed second origin of life, the universe becomes not a rare exception, but a fertile field. Planets stop being lonely. Galaxies stop being empty. Life becomes something the universe does, the way gravity bends light and stars fuse hydrogen. If the signals are stronger still, regular radio pulses, narrow band emissions, the spectral fingerprint of artificial megastructures, then the question shifts again. We are no longer asking, are we alone? We are asking, are we late? The possibility of a technological civilization in Alpha Centauri invites scenarios that feel as vast as the gulf between stars. Maybe they are ancient, watching us with the patience of a species that thinks in millennia. Maybe they are young, just beginning to reach for space as we are. Or maybe the hints of technology are ghosts, relics of a civilization that burned bright and vanished long before our ancestors walked upright. Each scenario carries its own philosophical weight. If we detect biology but no technology, Alpha Centauri becomes a natural laboratory. We can compare biochemistries. Are their proteins built from the same 20 amino acids? Do they use DNA or some other molecule to store information? Is evolution a universal mechanism, or something that can take radically different forms? The search for life on other exoplanets would shift from a broad survey to a comparative science. We would calibrate our telescopes and models against the closest example, then sweep the galaxy armed with a deeper understanding of what life can look like. If we detect technology, the search gains another dimension. The sky becomes a puzzle, not just of planets and atmospheres, but of intentions. We would comb exoplanets for power signatures, artificial illumination on the night sides, unusual waste heat patterns, the thermal glow of industry spread across continents. We would begin to map not only worlds, but cultures, however faintly and indirectly. Either way, Alpha Centauri becomes a Rosetta Stone. This discovery would also echo into how we think about the Fermi paradox, the apparent contradiction between a universe that seems hospitable to life and the fact that we have not yet seen clear evidence of advanced civilizations. If Alpha Centauri shows unmistakable signs of life or technology, the paradox deepens in one sense. If life is here and there, and likely elsewhere, why is the galaxy not obviously filled with super civilizations? One answer is the Great Filter, the idea that there is a barrier, maybe behind us, maybe ahead of us, that most civilizations never cross. If Alpha Centauri hosts simple life but no advanced technology, that might suggest that evolving multicellular, intelligent, or spacefaring beings is harder than it appears. Life may be common, but civilizations like ours could be rare, brittle, or short-lived. If, however, Alpha Centauri holds a technological civilization, the implications sharpen. The Great Filter might lie not in the emergence of intelligence, but beyond it, in the ability to survive technological adolescence, avoid self-destruction, or navigate cosmic hazards over millions of years. In that case, we would be looking not just outward for companions, but inward for warnings. There is another possibility. The paradox may not be a paradox at all. It might be an illusion born from limited data, like judging the size of an ocean from a single drop. James Webb and the telescopes that follow it are our first real attempt to look beyond that drop. Already, next-generation observatories are being planned. Giant segmented mirrors in space, telescopes positioned at gravitational balance points, instruments capable of isolating the faint reflected light from an Earth-sized planet and splitting it into a rainbow of information. We imagine star shades, vast petal-shaped structures flying in formation with telescopes, blocking a star's glare so that its planets can be seen as separate points. On the ground, 30 and 40-meter class telescopes will pierce the atmosphere with adaptive optics, turning distant systems into resolvable worlds. Each new eye deepens the question: is what we see around Alpha Centauri typical or special? If its planets are calm, life-rich, and perhaps even technologically active, then the night sky becomes a map of potential neighbors. If they are barren or hostile, with chemistry that hints at life's near misses, then each future detection of a promising world will feel more precious. In the stillness of the late hours, As the images from James Webb drift across our screens, we are left with a quiet realization. This discovery is not only about another star, it is about us. We stand on a small world, wrapped in a thin atmosphere, orbiting an ordinary star in an unremarkable arm of a galaxy among billions. And yet, for the first time, we are beginning to see the faint outlines of other small worlds, other thin atmospheres, other ordinary stars that may not be ordinary at all. Whether the signals from Alpha Centauri turn out to be signs of life, artifacts of strange physics, or simply the universe playing with patterns in our instruments, one thing is certain. We will not look at the sky the same way again. The distance between here and there has begun to shrink, not in miles, but in meaning. In that shrinking lies the true implication for humanity. The understanding that our story may be one of many, or one of a rare few, does not diminish us. It enlarges the canvas on which we draw our future. From this point onward, every telescope we build, every mission we plan, every question we ask about life and intelligence will carry the faint echo of Alpha Centauri. And the first time we truly began to see our cosmic backyard as more than just stars, it became a destination, and perhaps one day a meeting place. What comes next is not a single observation, not a single paper, but an unfolding campaign, a slow tightening of focus on a star system that has suddenly become more than a distant set of coordinates. It has become a question mark hanging over the night sky. In the wake of James Webb's first shocking glimpse of Alpha Centauri, astronomers do not simply sit back and marvel. They plan, they calculate, they prepare to turn this one strange result into a sustained investigation that could last years, even decades. Just as a spacecraft passing Jupiter uses that brief encounter to slingshot toward the outer planets, this first observation is only the maneuver. The journey is still ahead. The first step is simple in concept, but monumental in execution. Look again. James Webb will return its gaze to Alpha Centauri, not just once, but repeatedly. New observing programs are already being drafted, each one designed like a carefully tuned instrument. Some will focus on specific wavelengths of infrared light, looking for the faint fingerprints of molecules in the atmospheres of any planets that might be there. Others will map tiny changes in brightness over time, searching for patterns that repeat, vanish, then return again, like the echo of an unseen world passing in front of its star. Instruments on Webb that were once scheduled for broad surveys may now be reallocated for deeper, longer stares. Observing time on a telescope like JWST is precious, traded and negotiated like rare currency. But when a nearby star system begins to whisper secrets that shouldn't exist, priorities shift. Proposals are rewritten, schedules are reshaped. We point our most powerful eye back to the same tiny patch of sky, asking, did we misread the first signal, or is the universe truly trying to tell us something new? Webb will not be alone. On the ground, telescopes scattered across Earth are already preparing to join the watch. High in the thin air of the Atacama Desert, observatories like the Very Large Telescope, and in the near future, the Extremely Large Telescope, will turn their segmented mirrors toward Alpha Centauri. These instruments are not just big, they are precise. With advanced adaptive optics, they can bend and twist their mirrors hundreds of times per second, cancelling out the turbulence of Earth's atmosphere and sharpening their view of the stars. Where Webb sees in infrared, these giants can probe visible and near-infrared light, each wavelength offering a slightly different layer of information. Together, they form a kind of multi-dimensional vision. If a planet is there, if a strange atmospheric signature is real, If an unexplained fluctuation persists, these ground-based telescopes will help confirm it or challenge it. Array observatories like ALMA, tuned to millimeter and sub-millimeter waves, may join as well, listening not for starlight, but for the cold whisper of dust and gas. They can map the debris around Alpha Centauri, tracing the architecture of its planetary system the way a geologist reads the layers of rock in a cliff face. Is there a belt of asteroids? A cloud of icy bodies? Signs of recent collisions? Sometimes the environment around a star tells a clearer story than the star itself. In Hawaii, in Chile, in the Canary Islands, robotic telescopes and human-guided instruments will take turns watching. When one hemisphere turns away from Alpha Centauri, another turns toward it. The planet itself becomes part of the observing strategy, its rotation turning night into day at different observatories, stitching together an almost continuous stream of data. Above the atmosphere, other spacecraft will join the chorus. Hubble, though older, still has eyes sharp enough to refine measurements of stellar motion and brightness. Specialized missions like TESS, designed to hunt for planetary transits, can be directed to re-examine Alpha Centauri, searching for dips in light so small they might have been overlooked before. Future missions, still on the drawing board, already have a new target to add to their list. Beyond these immediate efforts lies something even more ambitious: the next generation of space observatories built specifically to find and study habitable worlds. Among them, one stands out like a promised future: the Habitable Worlds Observatory. It does not yet exist in metal and glass, but it exists on paper, in simulations, in engineering concepts being tested piece by piece. If built as envisioned, this telescope would be able to do something no instrument has ever done directly and clearly for a world like Earth. Take its picture. Not just a blot of light, a disk, a world. When scientists talk about the Habitable Worlds Observatory, they imagine it pointing at stars like Alpha Centauri, spreading the light of an exoplanet into a spectrum so detailed it could reveal oxygen, methane, water vapor, maybe even the faint chemical imbalance we associate with biology. To do this, it may use a star shade, a vast flower-shaped screen flying tens of thousands of kilometers away, blocking the glare of the star so the planet beside it can finally be seen. The first hints from Webb transform Alpha Centauri from a target among many into a priority. The plans drawn today could one day lead to an image of a small, pale dot circling our nearest stellar neighbor, a dot whose colors and chemistry carry the signature of clouds, oceans, or something stranger. But no single country, no single space agency can unravel this mystery alone. Just as no spacecraft reaches the outer planets without the help of Jupiter's gravity, no massive scientific discovery is reached without the pull of global collaboration. Already, the teams involved in studying Alpha Centauri span continents. NASA, ESA, and other space agencies share data, swap expertise, and coordinate schedules. Anomalies are checked not by a single group, but by independent teams using different methods. A signal that survives this process is stronger, more trustworthy, more real. New proposals will cross desks in Washington, Paris, Tokyo, Canberra, and beyond. Supercomputers in multiple nations will run parallel simulations, modeling everything from planetary orbits to atmospheric chemistry, each test like a trial run for reality. Radio observatories, optical telescopes, space missions, each with their own specialties, will synchronize their efforts, turning a once routine observation into a global campaign. In this process, there is no single hero, no solitary genius. There are thousands of minds, each contributing a piece. Some will question the original data, Others will defend it. A few will suggest radical interpretations. Most will test, refine, and challenge until what remains is not what we hope to see, but what we can no longer ignore. Science moves at a pace that can seem glacial against the speed of breaking news. The signal that shocks the world in a headline today may take months, even years, to fully understand. New JWST observations might be scheduled over the next 1 to 3 years. Ground-based follow-ups will stretch longer. Data analysis takes time. Instrument calibrations need to be checked. Biases must be hunted down. Then comes peer review, the quiet, relentless engine of scientific progress. Papers are submitted, critiqued, revised, sometimes rejected. Other groups attempt to reproduce the results with their own observations. Patterns that looked astonishing at first may fade under scrutiny. Some will survive. Those that do become part of our shared understanding of the universe. In the case of Alpha Centauri, realistic timelines mean that clear confirmation or refutation of the most dramatic interpretations could take 5, 10, or more years. To some, that delay feels like a disappointment. But to those who have watched missions like Voyager, Cassini, or Juno slowly transform our understanding of entire worlds, it is simply the rhythm of discovery. And yet, in this long, careful process, there is room for more than professionals. Modern astronomy is no longer confined to mountaintop domes and spaceborne observatories. It extends into backyards, school rooftops, and small observatories run by local clubs. Citizen scientists armed with modest telescopes, sensitive cameras, and careful patience can contribute in ways that would have been unthinkable a generation ago. Alpha Centauri is bright, visible even to the naked eye from the right latitudes. It is a perfect target for systematic monitoring. Amateur astronomers can track its brightness over time, compiling long-term light curves that may reveal subtle variations. While they may not detect tiny exoplanets directly, they can help flag unusual behavior, support professional observations, or provide independent checks on variability. Online, open databases of telescope data welcome volunteers who help sift through light curves, identify potential transits, or classify complex signals that machines struggle to interpret. In some projects, citizen scientists have already discovered exoplanet candidates, stellar flares, and even entirely new phenomena. Alpha Centauri will now join the list of targets where an attentive human eye might notice something everyone else has overlooked. In classrooms, students will simulate planetary orbits around a binary star. In living rooms, people will download public JWST images, stretching and coloring them, looking for patterns in noise. In forums and collaborative platforms, hypotheses will be debated, charts shared, possibilities weighed. From the most advanced space telescope ever built to a single person under a dark sky with a small scope and a notebook, the investigation of Alpha Centauri becomes a shared endeavour. A layered watch from orbit to backyard. The future of this mystery does not unfold in one dramatic reveal, but in a series of increasingly focused questions. Each observation, each mission, each late-night data run narrows the range of possibilities. What began as a shock may become a new normal, or it may remain an outlier, a puzzle that resists easy answers. Either way, the path forward is clear. We will keep looking. We will send more light through our instruments, more time through our detectors, more thought through our equations. And as we do, Alpha Centauri will slowly transform in our minds. From 3 bright points in the sky, to a mapped system of worlds, to, perhaps, something even more profound. The story does not end with what James Webb first saw. It begins there. The real journey, like the long arc from Jupiter's gravity assist to the edge of the solar system, is only just underway. We began, not among the asteroids or the gas giants, but in the quiet darkness between stars, looking toward a small point of light that to the naked eye seems unremarkable. Alpha Centauri, our nearest stellar neighbor, a familiar name in science fiction, suddenly transformed into something far less abstract. When James Webb turned its golden mirrors toward that system, what it revealed was not just data. It was a fracture line in our expectations. We saw worlds where we once saw only distant suns, subtle dips in starlight that betrayed the silhouettes of planets, faint signatures in their atmospheres that refused to fit neatly into our models, patterns of light and shadow that suggested activity, chemistry, and complexity where we had assumed a quiet, ordinary system. For some, the first reaction was disbelief. Instruments were checked, calibrations were rerun, software was re-examined line by line, and still the signals persisted. The journey from shock to understanding is never instantaneous. It is not a single eureka moment, but a long exhale spread across nights, weeks, and years. Early whispers of oxygen, methane, or unusual heat signatures do not immediately become proof of life or technology. They become questions. Why here? Why in this ratio? Why now, at our closest neighboring stars, and not first in some distant anonymous system? Each answer we attempt to give peels away one layer of surprise, only to reveal a deeper layer of mystery beneath. This is why what James Webb has seen around Alpha Centauri may become one of the pivot points in the history of astronomy. For the first time, we are not just speculating in the abstract about habitable zones and exoplanet atmospheres on the far side of the galaxy. We are probing the environment of the very stars next door. If there are worlds with unusual chemistry, strange thermal patterns, or even potential biosignatures there, then the concept of a lonely universe begins to feel less like a conclusion and more like an outdated assumption. Moments like this redefine the scale of our story. When Galileo first turned his telescope to Jupiter, moons became worlds. When Hubble looked at a seemingly empty patch of sky, thousands of hidden galaxies emerged. Now James Webb has extended that pattern toward Alpha Centauri, showing us that even the space just beyond our cosmic backyard may be richer, more complex, and more alive with possibility than we dared to imagine. Yet we stand, for now, in the era of maybe, of possibly and could be, and we don't know yet. The strange signals could be the fingerprints of unfamiliar geology, wild weather, or star-planet interactions we have not yet modeled. Or they could be the first hints of something far more profound, biological activity, or even technological behavior, leaving subtle imprints in starlight. To move from wonder to understanding, we will need patience, repetition, and above all, humility. This is where continued exploration becomes not just important, but essential. More observations with James Webb. Next-generation telescopes on Earth and in space. Dedicated missions perhaps one day, sent specifically to study the Alpha Centauri system up close. With each new instrument, we sharpen our view. With each new dataset, we test our assumptions. The universe is not obliged to be simple, and if we want honest answers, we must be willing to entertain possibilities that challenge our comfort. Open-minded inquiry does not mean believing every theory. It means refusing to close the door too early. Natural explanations and extraordinary ones must both be held up to the same light. Whether these signals from Alpha Centauri are the breath of alien oceans, the glow of industry, or simply the wild artistry of physics and chemistry, They are telling us something real about how the cosmos works. And that in itself is extraordinary. As you listen to this, you are part of this moment in history. Generations from now, students may look back on the first detailed observations of Alpha Centauri the way we look back on the first photographs of Earth from space, evidence that our perspective was about to change forever. Right now, we stand at the threshold, one foot in the age of speculation, the other in the age of direct observation of nearby worlds. If you'd like to keep traveling through these discoveries with us, through the quiet wonders and the shocking revelations, consider supporting this journey. Like this video if it helped you drift a little deeper into the cosmos tonight. Subscribe if you haven't already, and tap the bell so you don't miss the next chapter as new data from Alpha Centauri arrives. In the comments, share where in the world you're listening from. Together, we are a constellation of minds spread across a single small planet, looking outward. And if you'd like to go even further, you can join our YouTube membership to support the channel. It's completely optional, but it helps us continue exploring these questions in depth, night after night. For now, we leave Alpha Centauri not with conclusions, but with possibilities. Somewhere out there, in the faint glow of those neighboring suns, worlds circle in silence, unaware that a distant species has just begun to notice them. We are standing on the threshold of discovery, listening to the first faint echoes of an answer to a question humanity has carried for as long as we have looked at the stars. Are we alone? The universe has not yet spoken clearly, but for the first time, it feels as though it is about to.